A detailed look at seafloor spreading. A detailed look at seafloor spreading began in the 1950s when mid-ocean ridges were discovered using radar. Later in the 1960s, Harry H. Hess suggests seafloor spreading causes continental drift. Validity of seafloor spreading established by the identification and mapping of oceanic ridges, dating of volcanic rocks on the ocean floor, and understanding and mapping of the paleomagnetic history of ocean basins. Earth's magnetic field can be represented by a normal dipole magnet. The magnetic forces extend from north to south poles and is caused by convection in the outer core. The magnetic field has permanently magnetized some surface rocks at the time of their formation, as the iron-bearing minerals orient themselves parallel to the magnetic field at the critical temperature known as Curie point. Paleomagnetism is the study of magnetism of such rocks. Magnetic reversals have occurred throughout the history of our Earth. Some volcanic rocks show magnetism in an opposite direction as compared to the present. Because Earth's magnetic field has reversed, the cause of the reversals are not well known. They appear random and occur on average every few thousand years. The picture depicts normal and reversed polarity for our Earth. Magnetic stripes were found when geologists towed magnetometers along the ocean floor. The magnetometers are instruments that measure magnetic properties of rocks. When mapped, the ocean floor had stripes with areas of regular and irregular magnetic fields. The stripes are parallel to the ocean ridges, and the sequences of stripe width patterns match the sequences of paleomagnetic history established by geologists on land. This picture shows normal polarity in black and reversed polarity in white, paralleling the mid-Atlantic ridge, and the parallel pattern is fairly symmetrical across the ridge. This image shows how the stripes of polarity formed at the divergent plate boundary and then moved away from the boundary and more stripes formed, which in turn also moved away from the divergent plate boundary. Using the magnetic anomalies, geologists can infer ages for the ocean rocks. The seafloor is no older than 200 million years old. Spreading at the mid-ocean ridges can explain stripe patterns, where rising magma at the ridge is extruded, and the cooling rocks are normally magnetized. Previously, the field was reversed, but the new rocks have pushed the old rocks away, and the cycle repeats. This picture depicts the age of the ocean floor. You can see the youngest rocks are closest to the divergent plate boundary, and the oldest rocks are the farthest away from the divergent plate boundary, ready to be subducted at a convergent plate boundary. Hotspots are not related to plate boundaries. They are volcanic centers resulting from hot materials from deep in the mantle. Materials move up through mantle and overlying plates. Hot spots are found under both oceanic and continental crust. As depicted in the picture, the plates move over the hot spots, creating a chain of island volcanoes, where the magma chamber remains relatively stationary. Seamounts are submarine volcanoes. Some famous examples of hotspots are the Hawaiian island chain and Yellowstone. Here is a picture of the Hawaiian hotspot and the lengthy island chain it has created. Note the bend in the chain at about 43 million years ago, when the Pacific Plate changed its direction of movement from more north to more northwest. The island chain sinks and is eroded to become seamounts, underwater islands, that stretch all the way to the convergent plate boundary by the Aleutian Islands between Alaska and Russia. The islands and seamounts increase in age away from the hot spot. Here is a picture of the Yellowstone hotspot as it has melted through the North American continental crust. Again, the resulting calderas increase in age away from the hotspot. Ages are indicated in millions of years. Can you tell which way the North American plate is moving relative to the stationary hotspot? Did you think southwest? 2.4 Pangaea and present continents. 2.5 How plate tectonics works, putting it together. And 2.6 Plate tectonics and hazards. Plate tectonics explains both continental shape and the location of mountain ranges. Movement of plates is responsible for present shapes and locations of continents. 180 million years ago, there was a breakup of Pangaea, which was a supercontinent extending from pole to pole and halfway around the Earth. 50 million years ago, India crashed into China, creating the Himalayas. These pictures show map snapshots of the major continents at 180 million years ago, 135 million years ago, 65 million years ago, and 0 million years ago. Those continents have sure zipped around. The theory of plate tectonics has solved several geologic problems. Reconstruction of Pangaea and recent continental drift clears up fossil data difficult to explain with separated continents, as depicted in this picture. Land animals and plants that exist as fossils on several present-day continents used to be on the same megacontinent. Phew! No marathon swimmers needed. Reconstruction of Pangaea also clears up evidence of glaciation on several continents, and illustrated in this picture. Without the theory of plate tectonics, those glaciers would need to spread inland from the coast, a very unglacial thing to do. But if Pangaea, especially southern Gondwanaland part, is put back together, many of our current coasts were landlocked, and the glacial spreading pattern matches up nicely. The driving mechanism for plate tectonics has two parts: ridge push and slab pull. Ridge push refers to the massive mountain ranges that are at the divergent plate boundaries, as at the mid-Atlantic Ocean ridge. Gravity pulls down on this mountain range, which would push the lithospheric plate to the convergent plate boundaries. Slab pull refers to the ginormous subducted lithospheric plate falling by gravity into the mantle, pulling the surface lithospheric plate down with it. Evidence suggests that slab pull is the more important process, though ridge push probably helps too. It's just that the subducted slab is so much bigger and extends so deep into the mantle that the massive ridge-mounted ranges are kind of small in comparison. So, why do we need to understand plate tectonics to understand natural hazards? Can you think of any reasons? I think you'll need to for the quiz. Wink, wink. There are both direct effects, like what happens with plates move and melt, and there are indirect effects, like what happens when a mountain is built and then erodes, or blocks rain, or catches rain, etc. Get creative, but be able to reasonably and clearly explain your creativity. Have fun until I talk to you again in Chapter 3. We get to learn about earthquakes.